Hello everyone, I am Shruti Tokle, Senior Researcher in the Confidential Computing team at MSR Cambridge, UK, and today I'll present how causal learning approaches can provide better privacy guarantees for machine learning models. First, let us understand what is the privacy concern with state-of-the-art machine learning models. ML models are known to leak information about training data, which becomes a serious concern in some sensitive applications. For example, consider a hospital that trains a neural network for predicting a disease with health records of HIV patients. When this model is exposed as a service to other hospitals, an adversary can guess whether a person was in the original train set by just observing the output scores. Such attacks are called as membership inference attacks and pose a serious threat to the privacy of users participating in the model training. The likely reason for this membership inference attacks is that neural networks, or associational models, in general overfit to the training set. For example, on the right, the ML model's accuracy decreases when it is evaluated on the test set. Further, neural networks have the additional problem of overfitting to the trained distribution as they fail to generalize to unseen distributions. Prior work has shown that membership inference attacks exploit this difference in prediction scores or the generalization gap, allowing the adversary to accurately identify members of the training set. On the other hand, causal learning approaches are gaining attention for their generalization capabilities. Under the common assumption that distribution of causal features remains invariant in naturally occurring data, prior work has shown that causal learning approaches generalize well to unseen distributions. With the understanding of reasons for membership inference attacks and generalization benefits of causal learning, we now ask whether causal learning can improve the privacy guarantees of machine learning models. And the answer is yes. The key reason is that the better generalization capabilities make causal models less sensitive to contribution of a single training point and thereby exhibiting strong epsilon differential privacy guarantees, where sensitivity is defined as the maximum possible change in the learned model parameters when a single data point is added or removed from the training dataset. And differential privacy, which is the strongest notion of privacy guarantee, ensures that the ratio of probability for a mechanism attaining particular model parameters on datasets that differ by a single sample is bounded by epsilon. So, smaller epsilon values provide better privacy guarantees. One way of designing epsilon differentially private mechanism is to add noise proportional to the sensitivity of the algorithm. This leads to our first theoretical result that when equivalent noise is added to models trained on the same dataset, a causal mechanism will exhibit stronger DP guarantees as compared to an associational model. That is, epsilon for the causal model, epsilon c, will be less than or equal to the epsilon of an associational model. Prior work has then connected that epsilon value of a DP mechanism provides an upper bound to the membership inference advantage of an adversary. Hence, we have our second result that for models trained on the same dataset of size n, membership inference advantage of a causal model is lower than that of an associational model. For detailed proof, you can look at the paper. Now let us look at some empirical comparison of privacy guarantees of causal and non-causal models in three different settings. We first look at a single party setting where the true structural causal graph is known. For models trained for prediction on the child dataset with X-ray report as the output variable, as you can see in the graph, we see that the attack accuracy for causal model comes to a random guess, that is 50%, while that for a non-causal model is up to 80%. We observe that causal models provide better resistance to membership inference attacks while attaining the same utility as associational models after convergence, thereby providing better privacy without loss in utility. For the multi-party setting, we do not assume that the structure of the causal graph is known. Here, we rely on a domain generalization method based on causal learning that we recently proposed called Perfect Match to learn a model on Fashion-MNIST dataset. In this setting, we assume that each party contributes data corresponding to a different domain. Example, a different rotation of angle for the Fashion-MNIST dataset. From the graph, we observe that for the same epsilon differential privacy guarantees, causal model provide better utility as compared to the standard ERM-based non-causal model. Additional results on other datasets, as well as membership inference attack results, are available in the paper. Lastly, we look at generative models that are often trained on private data to create synthetic data to be released for public use. However, these models are susceptible to membership inference attacks as shown in prior work. The graph on the right shows that for the same epsilon dp guarantees, synthetic data generated from a causality-aware generative model provides higher utility for downstream tasks as compared to a non-causal model. To conclude, we have established theoretical connection between causal models and differential privacy. We have empirically confirmed the benefits of causal learning for privacy in 3 different settings. These results show that leveraging causal learning techniques is a promising direction to balance privacy utility trade-off in the ML models. Last but not the least, I would like to thank my amazing collaborators who have contributed to the research presented in this talk. Thank you.